Hello everyone, it's Nay here and welcome to another episode of Knowledge Dump. In this one we're looking at the proton, the neutron and their other friend, the electron. Basically we're looking at the atom. Let's get into it. Key definitions that I'd like to run through. So atomic number is the number of photons, mass number of photons plus the number of neutrons. Basically it's the weight of an atom. An element is something made out of one type of atom. An ion is a charged atom, which is either a cation, positive, or anion, negative. An isotope is the same element, which means it has the same number of photons, but with a different mass number, which means it has a different number of neutrons. On the periodic table, where element is displayed like this. So this is oxygen, you have the atomic number on top, 8, the chemical symbol, O, the relative atomic mass, 16 in this case. We'll get to atomic mass in a second. Oh, actually, I'll explain it a bit now. So basically, the relative atomic mass is the average mass of all the different isotopes found of oxygen on the planet, and like kind of averaged out to that. And the element name, of course, oxygen. So first thing we're going to look at is isotopes. So on the left, you can see 3 different isotopes of hydrogen. There's one with one photon and no neutrons, which is just your regular hydrogen. And then there's one with a neutron and a proton, one with 2 neutrons and a proton. So those are 3 different hydrogen isotopes, but they're all still hydrogen because they all have 1 proton. You can see next to each of the names, protium, deuterium, tritium, is what we call the nuclide symbol, and that's how isotopes are usually displayed. So up top you have the mass number, so in deuterium's case it's 2, and below it you have the atomic number, which is 1 for hydrogen. And then beside that, of course, you have the chemical symbol. Radioisotopes are radioactive isotopes of specific elements. They're basically atoms that contain an unstable combination of neutrons and protons, or excess energy in their nucleus, making them highly unstable as well. Yeah, that's how radioactive stuff happens, I guess. Okay, the next thing we're going to look at is electrons, electron shells. So there are 3 rules to follow with electron shells. So each electron shell holds a different number of electrons. The electrons will fill shells closest to the nucleus first, because that's the highest energy level, and the electrons will fill empty shells in a particular order. So below we have a table of the first 4 shells. In shell 1, it can hold a max of 2 electrons. In shell 2, 8, and 3, 18, and 4, 32. In the next slide, we'll see this is the Bohr model, which is basically a simplified version of other models of atoms, electron configurations. Basically, it narrows it down to shell, just like the main shells. And how you can work out how many electrons can go in each shell is that formula there, 2n squared, where n is the shell number. So say for shell 3, n squared is 9, 9 times 2 is 18, so that shell can hold a maximum of 18 shells. However, it gets a bit more complicated when you look at how we fill these shells. Atoms are most stable with a full outer shell, so that's like the octet rule. 8 shells, like in 8 electrons in a shell, makes a stable atom. And like atoms that only, I guess, close to that are highly unstable because they really want to become stable. This might not make much sense, but you'll see later on. So the periodic table is split up into 4 different blocks. You've got the S block, which includes groups 1 and 2, and also helium on the top right. The P block, which includes groups 13 to 18, excluding helium, of course. And then the D block, which is all your transition metals, and the F block, which are the lanthanoids and actinoids, or whatever they're called, that like reside below the periodic table. This is called the Schrödinger model. So it's basically a more detailed model of the Bohr model. The Schrödinger model believes that electrons are not fixed. They are found in orbitals around the nucleus, and each orbital can hold 2 electrons. And also electrons fill the lowest energy level first, which is the closest to the nucleus. Okay, so your 4 types of subshells above, the S, P, D, F, they each hold a different number of orbitals again. There's a lot of different numbers you have to remember here. So the S holds 1, the P block holds 3, the D subshell holds 5, and the F holds 7, which means that the maximum number of electrons is just double those amount of orbitals, 2, 6, 10, and 14. You just remember them as odds and then times them by 2. You can also remember all this is like kind of like a flowchart from greatest to least. So shell, well, you have the atom first, and then you have the shells, which are the general areas of energy levels that go out from the nucleus. You have the subshells, which are the energy levels within those shells. The orbitals, which are the regions inside the subshells, and the electrons reside inside, which the electrons eventually reside inside of. And on the far right there, you can see an energy diagram. So the electrons don't fill shells always fully. You see the first two, it fills the first one fully, and then the second one fully, and the third one fully. But the third one, it fills a 4 shell first before coming back to the third one after 4s. Yeah, just kind of remember it like draw it out and remember it like this. Basically, this is how electrons fill up. And this is an example of the notation of them. So here we have atom of magnesium, which is stable, so it has 12 electrons. Well, not stable. Well, okay, there's a lot of different stables, but it's a neutral atom. It's not an ion, so it's got 12 electrons. The first number is the shell number, the second letter is the subshell, and the superscript is the number of electrons. And at the end there, we have the valence electrons, like in this case 3s2, so the two electrons on the third shell. This is another look at the subshell model. So you can see with the number of shells to the right, the subshells. So the first shell only has an S subshell, the second shell has an S and a P subshell, the third has an S, P, and D, the fourth has an S, P, D, and F, and the others also have all 4. And you can see the numbers on the right relating to number of orbitals in each subshell and maximum number of electrons. The last thing we're going to cover is excited electrons. So electrons, when they receive atoms, when they receive energy, their electrons jump out to further out shells. They jump to higher energy levels, basically. And they also emit light. Like, think of putting magnesium in a Bunsen burner. It emits a really bright light. And that's not because of the energy that's put, well, it is the energy that's put into the atom, but it's when the atom falls back to its ground state. So an atom will only stay in its excited state for a short period of time. Think of like I'm not sure, like an excited puppy. He's only gonna run around for so long before he eventually just crashes and sleeps for the rest of the day. The atoms are the same. They can only remain in that excited state for a period of time before falling back to the ground state. And when they fall back to their ground state, since energy cannot be destroyed or created, that's the energy law, that excess energy is released as light. And depending on the element and the amount of electrons, that light emits kind of different wavelengths on the light spectrum, producing a different color. You'll see this in if you ever do flame tests or color tests. It's a popular fact for this topic. Yeah.